Hello friend, welcome to lambda by 2. So it is a open-ended wire. So you can see here the is given. You can see here there. We have made a model of new report. So you can see exactly at 3 degree and 1 degree step size. This is polar plot. So this is the 3D polar plot. Next I want to see this is the radiation pattern along XY, your bidirectional radiation pattern. This will be our polar plot. Next see here, this is our that we have already seen. This is the radiation pattern we have. Hello friends, welcome to the antenna design and simulation tutorial. The first tutorial is on dipole antenna. I am Dr. Balwant Makwana. So basically a dipole antenna is a wire antenna whose length is equal to lambda by 2. So it is a open-ended wire. So you can see here this is the dipole antenna whose length is equal to lambda by 2, and this shows the standing wave pattern. You can see that since this is an open circuited end, so at this end the current is 0. It means the voltage will be maximum and it is fluctuating according to the sinusoidal power given at this end. We are assuming that at this end this will be act as a short circuit, so current will be maximum at this point and voltage will be minimum. So this is the standing wave pattern observed in the dipole, and this is the dipole in receiving mode. So you can see the electric field is coming here and it is generating, it is inducing the voltage on the. So to design a dipole antenna in any simulation tool, like we are going to use HFSS, that is high frequency structure simulator, so we require basically three things. First one is the dipole length. This will be equal to lambda by 2. The second one is feed gap. What will be the distance between the two arm of the dipole, that is called as a feed gap. And third one is the dipole radius. So let us take frequencies f. So wavelength will be naturally equal to c by f, and the dipole length we are taking approximately 90 to 95% of lambda by 2. Why? Because impedance of dipole is around 73 plus j45. So we want to reduce this j component. In order to reduce this j component, we have to decrease the size of dipole to around 5 to 8%, so which will give our approximate dipole length is equal to 90 to 95% of lambda by 2. And dipole radius we are taking small radius up around lambda by 8. So let us take, I want to design a dipole for 3 gigahertz. Then my wavelength will be 3 into 10 raised to 10 divided by 3 into 10 raised to 9. We have taken 3 gigahertz because the calculation will be easy. So 3 divided by 3, so that will give us 10 centimeters. So wavelength is equal to 10 centimeter and length is equal to lambda by 2, and dipole length will be equal to 90% of lambda by 2. It means 90% of 5, that will be equal to 4.5 centimeter. So and we are taking radius is equal to lambda by 80, so that will be equal to 0.125, and feed gap once again we are taking 0.125 centimeter. To design this we have to go to HFSS. So this is our HFSS, and so to have any project in HFSS, these are the mandatory step in a HFSS. So first of all we have to make a 3D model. The 3D model we can either import from any 3D software, or we can make this 3D model by using this component given in HFSS. So first of all we'll take the component that is called as a cylinder, because we want to have a 2 cylinder, one at the top and one at the bottom. That will be our dipole. So we'll draw our model. I am having a cylinder. I will place anywhere in my coordinate system. I want to draw it along z direction. My length of the dipole should be along z direction. So I am taking, by default it will take whatever the solid will be there. By default material will be vacuum. Before drawing anything we will choose from modeler, go to modeler, and we'll choose the unit. In unit we will take our default unit is mm, but we'll change this to centimeter. So now the unit will be centimeter. We have drawn the cylinder and I will now give its coordinates. So by default whatever the coordinates will be there, it will come here, Now I want to change this coordinate because I want to change the size and shape of this cylinder. So I will make, because my length of the cylinder is 4.5 centimeter, so upper arm will be 4.5 divided by 2, and I will start from 0.125 that we have calculated. So first of all, along y axis, so this is also equal to 0, and along z axis, z is equal to 0.125 divided by 2, and the radius we have already calculated, that is 0.125, and the height of the cylinder, that is 4.5 divided by 2, because we have calculated the height or the length of cylinder. The length of upper arm of dipole will be equal to 4.2 centimeter. So you can see here, this is for upper arm of the dipole. I will click OK. So this will make my dipole, and to fit this model in this window, I will click here. So you can see that the upper arm is there. Now I want to make same arm in bottom side, so there are some facilities, like I will click here, I will copy the same cylinder and I will rotate it around y axis 180 degree. So for this we are having option, you can go to, and this will be enabled. So I will click here. So these options are available. So I will select this one, that is duplicate around axis. So I will choose y axis, this is duplicate around axis, and along y axis I will rotate this 180 degree. So it will duplicate the same arm. You can see here the same arm is duplicated, and there will be 180 degree, and the gap you can see there is 0.125 centimeter gap is there. Now in this gap have to feed some power to this dipole. This gap will act as a port. In order to make this port, we have to assign some object here. So for this I will assign a rectangle at this location, change the coordinate system by, because right now it is in xy coordinate and I want to make the rectangle in yz coordinate. So I will click here and there will be yz code. Now I will click on rectangle. I can draw a rectangle anywhere and I will give the coordinates, or you can directly choose this to edge and you can click over here. This will produce a rectangle. This is not a perfect rectangle because I want at these edges, so I will give the coordinates to this rectangle, the same coordinates as the earlier one. So let us copy this coordinate, or I will give new coordinates. So this will be equal to radius. So radius along, so you can see here, this will be equal to, along y I will have a radius, or so this will be equal to, x is equal to 0, y is equal to, what is our radius, that is equal to 0.125. it will start from minus 0.125, and what will be the height, it will start from minus 0.125 divided by 2, minus 0.125 divided by 2, because we have taken this complete height is equal to 0.125. so this much upper height will be 0.125 by divided by 2, and this height will be equal to 0.125 divided by 2. So we are starting at this location, that is y is equal to minus 0.125 and this height is equal to 0.125 divided by 2. We want our along y axis, my length will be equal to 2 times this 0.125, right? So it will be 0.125 into 2 into 0.125, and along z axis that will be equal to 0.125. so minus 12.5 by divided by 2 divided by, so overall length is equal to 0.125, and here the overall diameter will be equal to 2r, so this will be 2.125. so you can see that now this rectangle is completely fixed here. Next I will assign some material. So you can see that the model is created. This is your model. I will change the color by double clicking on rectangle. I will change this color to, let us take this red color, right, and I will make somewhat opaque. Okay. So this will be our dipole antenna. This is model. Right now we have not given any material to this. So first task is completed, that we have completed our model. Next is we have to assign boundary, or you can say we have to assign material to whatever the 3D object we have created. So So I will click on cylinder, and for this cylinder double click here. You can click here, or the second option is right click on cylinder, and there is property called assign material. So assign material, I will choose some material. Let us take, I am choosing aluminium, so this will be your aluminium. I will choose OK. The bottom one is also a aluminium, so I will right click here and assign material. I will write aluminium once again. So this is my aluminium, and I will choose this. So these two are assigned as a aluminium, and this sheet we want to assign this sheet as a port. So I will click on this sheet. I will right click here, and I will choose as assign excitation. So I will give this as a lump port. So there are various kinds of port, like wave port that we are giving to the waveguide, then flockhead port, incident wave. Right now we will choose a lump port, whose resistance is 50 ohm. To assign a port, we have to give the reference integration line. It means reference direction of electric field. So let us take, we have to assign this. So click on none. It will give option for new line. So for new line you have to choose from bottom to top of the rectangle. So it will show the arrow along the Z direction, and it will show the define. Then click next and finish. So our first thing is done. The second thing, there is boundaries. Either you can assign boundary or you can assign material. There is also complete. Then we have done the excitation. You can see at this port, and this is excitation is complete. Right, the next operation will be done by this software automatically. You can also do manually. Next thing is analysis. One more boundary is remaining, that is called as radiation boundary. So within this boundary, it will calculate the electric field and magnetic field and apply Maxwell's equation, and overall it will find out the electric field and magnetic field. From that we can find out any other component. So we will define a radiation boundary which will be at least equal to lambda by 6 from the radiating aperture. So you can do directly by click on this box, which will create a region. I will select the second option, that is called absolute offset, and I will select the value is equal to 1.5 centimeter. So from each and every point from the antenna, it will create a box which is 1.5 centimeter away from the antenna. So it will generate a box. You can see here, this is the box it has generated. So from each side this will be equal to 1.5 centimeter. This should be approximately equal to lambda by 6 from the radiating structure. As soon as box is there and the by default material of the box is vacuum, we are going to change this material, and we are making this box as a radiation boundary. So I will choose my box, I will right click on this region, and I will assign this as a radiation boundary. Assign boundary, go to radiation boundary and click on radiation. So click on OK. So you can see here the boundary is there. We have made a model, we have given all the boundaries and material, then we have done the excitation. Next is the mesh operation. Mesh operation will be done automatically by the software. We can also do manual operation, but right now we are not going to do this. The next operation is analysis. So in analysis we are going to give the frequency of operation, and we will give the band on which it will simulate. So first right click on the analysis and add solution setup. So my solution frequency is 3 GHz. So I will write 3 GHz here, and rest of the thing will be default. So I will choose OK. Next I want to give the band on which we want to see the simulation results. So I will click on setup. I will right click here, and there is option for add frequency sweep. So I will click on add frequency sweep, and there are some option for sweep tab. Basically there are 3 different sweep tabs. There is interpolating, fast and discrete. So interpolating is least accurate, then there is a fast, and then there is a discrete. Discrete will have a maximum accuracy, but right now we'll choose the interpolating because we want the fastest result will be given by interpolating. I will keep my frequency from 2 to 4 gigahertz, or I will choose from 1 gigahertz to 5 gigahertz, and I will take the step size is 0.01. so you can see these are the frequencies at which we are going to plot. So I will click on OK. So my band is from 1 to 5 gigahertz. I want to observe the pattern. Analysis is over. Next is optimetric. So if we want to optimize our model, we are going to use optimetric. I am not showing optimetrics right now. The next is result. To calculate result, we have to run this model, and to run this model, first we have to validate the model. So I will click here. This is for validation. So I will click here. If there will be any error, then it will show the error and there will be red color cross mark. So I will close this. Next, I want to run my model. I want to analyze my models. There are various options for analysis. You can right click on analysis, and there is option for analyze all. You can also right click on HFSS, and there is option for analyze all, or there is option here, direct button is there for analyze all. So I will click on this button, there is analyze all, and it will ask for the name and directory, and we want to see the result. For the result, we have to give the simulation is over, and in result we have to see the S11 parameter. So I will click on result. There are some options are there. From this option I will click on rectangular plot, and it will automatically choose S11, and I want to see the S11 in dB. So I will click on new report. So you can see exactly at 3 gigahertz we are getting our resonance. Now what do you mean by S11? S11 is, we are considering this is a antenna as a 2-port device, where port 1 is our input port and output port, that will be antenna. Whatever power we are feeding to port 1, all the power should be radiated by the antenna, so no power should be reflected back. So S11 is, we are feeding power to point 1 and we are measuring at the same port. If there will be reflected power, then that power will be measured. So this should be minus 10 dB down, and we can see at 3 gigahertz we are getting around minus 11.75 dB. So it is resonating at 3 gigahertz. This antenna will work at 3 gigahertz. Next, we want to see the far field pattern. So in order to see far field pattern, right now you cannot see the far field pattern. There are no option for far field pattern. For this we have to set up a infinite sphere, and that you can do by right clicking on radiation and choosing insert far field setup. So I will click on infinite sphere, and I will give the values of theta and phi. Theta is equal to 0 to 180 degree and 1 degree step size. Phi is equal to 0 to 360 degree and 1 degree step size. This is for 3D polar plot. So I will click on right click here into result. Now the create far field will be there. Otherwise, if I will not give the radiation boundary or infinite sphere, then this far field report will not be there. So I will click on 3D polar plot. I want to see the 3D pattern. So I will click gain total, and I will click on dB, and I will select new report. So it will calculate the 3D polar plot. So this is the 3D polar plot. Next, I want to see this plot. I want to cut along XY plane, and I want to cut along XZ plane. So XY plane we are having phi coordinate, and in XZ we are having theta coordinate. I will once again introduce one more infinite sphere. I will right click on insert far field setup. I will click on infinite sphere, and I will introduce one more infinite sphere, that is infinite sphere 2. I will change the theta coordinates. So I will change theta from 0 to 90 degree, and I will keep this as it is, and I will only change the step size. So what it will do, it will take the theta value from 0 to 90 degree only. So this will take only from 0 to 90 degree. Next 90 to 180 it will not take. So it will cut from XY axis. So there will be cut from this angle, XY plane. I will click OK. Right click here. Once again I want to see the 3D polar plot, but I will select geometry is equal to infinite sphere 2. I will select gain total, dB, and I will click on new report. So you can see this is the radiation pattern. along xy axis. In xy axis it is behaving as omnidirectional antenna, because at each and every location this is the pattern is equal to circle. It means it is radiating equal power in all this direction. Now I want to cut my radiation pattern along theta axis. It means along xy axis. Pattern I will insert one more infinite sphere. Is now theta as it is, and I will change the phi. Phi is equal to 0 to 180 degree, and I will take 1 degree of step size. So what it will do is it will take phi is equal to 0 to 180 degree. Only half portion will be there and rest of the portion will not be there. So it will take a cut along the xz plane. So once again I will go to result. I will click on far field pattern. I will choose the 3D polar plot. I will choose the gain, and in gain I will choose dB, and I will select infinite sphere 3, and I will click on new report. So you can see here there will be cut in xz plane. It is bidirectional radiation pattern. To make this smooth, I am taking a step size is equal to 1. So this will be your bidirectional radiation pattern. I want to see the linear pattern, or you can say I want to see the rectangular pattern of this. For this I will choose phi is equal to 0 to 90 degree, and I will take the step size is equal to 90 degree, and theta is equal to minus 180 to 180 degree, and I will choose step size is equal to 1 degree. Now I will click on result. I will click first, I will plot the polar plot. So I will click on radiation pattern for polar plot. Gain, I will choose gain total, and dB I will choose infinite sphere 4, and you can see this will be our polar plot. Next I want to see the same thing in linear plot. So I will click far field, and now I will choose rectangular plot, and in rectangular plot I will choose the same thing. Once again I will geometry, I will select infinite sphere 4, and I will click new report. So you can see here this is our rectangular polar plot. I can find out the maxima by clicking in this add maximum marker. I am adding this marker. I will click here. So you can see this, the gain of antenna, this lambda by 2 antenna is equal to 1.7177. in theory also you are going to learn that the gain of dipole antenna is 1.7 dB. So this is all about dipole. I will select this pattern. You can right click to this image, copy image, and you can paste wherever you want to paste in your report, either in Word file or in PowerPoint presentation file or wherever. These are the things. I am going to paste this in a PPT that I have shown you. So after placing this, these are the plot we have already generated and we have seen. You can see I have taken this plot from our simulation. This is at 3 GHz we are getting this, and these are various polar plot that we have already seen. This is the radiation pattern we have seen, and this is our linear plot. So this is how you can analyze any dipole antenna. This is the approximate analysis, and approximate analysis also give us somewhat accurate result, that is 2.99 GHz. We have designed for 3 GHz and it is resonating at 2.99 GHz. Thank you very much. For any doubt you can contact me on my email address which is given here, that is antenna.designer.simulator@gmail.com. Thank you very much.